Okay, hello everyone. Thanks for joining to the Western Session 6. This session is about traffic prediction, simulation, and computational methods. We have 6 presenters in this session. Each presenter has around 15 minutes time, and we will have 3 to 5 minutes of question and answer after the presentations. I would like to start with our first presenter, Dr. Mahmoud Hishmat. He is a researcher specializing in industrial and manufacturing engineering. He's affiliated with Ningbo, China Institute of Supply Chain Innovation, MIT Global Scale Network, and he's an associate professor at the Department of Mechanical Design and Production Engineering at Asyut University in Egypt. Today, he's going to present his work on AI-driven disruption-aware transportation systems framework. Dr. Hishmat, please feel free to share your screen if you are here. I don't see.
Yeah, I already sent an email, so I don't think he's here now.
Okay. Okay. I'm sorry.
So I think our next presenter is present, like the Silvano Barbel. We can start with her.
Yeah, we can start with Silvano. Silvano Bernabel is a data scientist working in AI research and is
I
a
will let you decide on this. I just finished my presentation from the last session, so
okay. I'm confused.
Sorry for the disturbance.
So who was that? I couldn't follow the who was talking.
So
We cannot hear you, Arna.
So it would be Silvano Barnabel.
Okay. Okay, we'll start with Silvano. So Silvano Bernabel is a data scientist working in AI research and a PhD candidate in computer science at the Graduate Center of the City University of New York. His research focuses on the intersection of generative AI and complex systems. Today, he's going to present his work on multi-cluster correction method for parallelizing large discrete event simulations. Silvana, please feel free to share your screen and start your presentation.
Hi, can everyone hear me?
Yes, we can.
Well, I have to share my screen, yes?
Yes, please.
Okay, I thought you were going to share the... Give me a second. I wasn't prepared for that.
So in the meantime, to the audience, if you have any questions, please enter your questions into the chat box. And I will ask the presenters at the end of their presentation if they need any explanation. You can unmute and discuss about it with the presenters.
Sorry. Okay. Um, I have to, I'm so sorry. I have to restart the Zoom.
Do we have any other presenter who is ready to
It'll take a second.
I think we have the Abigail Wheelis. So
I would like, is anybody ready to present in the beginning? We will welcome.
Hi, Dr. Fatemeh. I'm also available if you want me to present here.
Okay. So I couldn't follow who talked, and I think Abby is available and
I'm available again. Sorry.
I'm Nafees. I'm also available to present.
Okay.
Thank you.
So we will start with probably Abby. Can you start sharing your screen and start your presentation? I will introduce you.
How does that look?
Okay. Yes. Yeah.
Okay.
We can see your screen. Abby is a researcher in National Laboratory of the Rockies. Her work spans data collection, analysis, model improvements, testing, and community engagement. Today, she's going to present her work on calculating energy estimates on routes. Please feel free to start, Abby. Thank you so much.
Okay. Hi, everybody. Thank you for the introduction. I'll be presenting today, but a couple of my colleagues who worked with me on the project are present, so hopefully they'll be able to jump in and answer your questions as well. And we will be representing the National Laboratory of the Rockies today, talking about our calculation method, CHEER, for calculating holistic energy estimates for routes. We frame this as an energy meter for transportation related to an individual. We'll go over a detailed use case from our open source application, the National Laboratory of the Rockies OpenPath. I'll just refer to it as OpenPath for ease from here on. Go over CHEER, improved estimation that we developed in 2024, talk about some of the results and impact of these new calculation methods, and then ways that we could continue to improve them. So this is a list of some of the methods or apps that we gathered from the literature who claim the goal of providing an energy meter for individuals. Maybe this is for the ability to optimize them for things like cost or energy efficiency, and would function similarly to the way the electrical meter on your home operates. I know I've been watching that very closely during the heat wave as I need to run AC more than I usually do. But we host NLR OpenPath, which is an open source application that anybody can use. You would be welcome to download it onto your phone today and join the open access study to try it out for yourself. It's been used by more than 40 organizations, both in the US and abroad, for collecting data on various transportation programs. We'll start with our simpler approach, which was very aligned with what is present in the literature. Which takes a simple multiplication of the distance of the trip by some sort of estimated energy factor or emissions intensity. You can see here some screenshots of our app. On the left, we have the travel diary page where trips are automatically recorded in the background while your phone is being carried around in your pocket. And then you're able to go back in and add labels to that trips to enhance the modes that we're able to sense from just the patterns of motion of your phone. On the right, you can see the in-app dashboard showing users their energy usage and estimated footprint for a time period. And then in the center, we have the online program-wide dashboard that can be used by the public or program administrators to look at various aspects of that program, including the total energy and emissions estimates. This does come with some challenges, though, as I'm sure many of us are familiar. Classical travel survey data is often provided with paper surveys or calendars where people are asked to estimate the distances of their trips and recall the modes they took. just off the top of their heads. I know if you asked me how long it took me to get to work, it would vary greatly by whether I biked that day or drove that day or which route I took or which route had traffic on it. And it would be a very rough estimate of the distance. We've solved for this problem by installing odometers onto our vehicles or onto bikes so you can see how long trips actually are, but those are just for individual modes. So we can link together between modes by using smartphone data, as we're all already carrying around these phones in our pockets. It can also be difficult to estimate the energy factor. So it can be hard to distinguish between modes. The motion patterns of your phone bouncing around in your pocket are pretty much the same as they are on a bike as they are in an electric bike or, electric car. We can also have variations in efficiency between models of a given mode. It's very different, the efficiency of a very new hybrid car versus an older gas car, but those are going to look the same on paper most of the time. Differences in load factors or number of passengers. This matters for transit data as well as for, carpooling. We all know that it is a more energy efficient choice to carpool than to drive by yourself. There's signs all over Denver where I am now to carpool because we're having heavy ozone from some wildfire smoke. But fleet composition also matters. Things like electrification of transit. You see a picture of an electric school bus here. As that progresses, how are we able to keep up with estimating the impact of that on a program level or on an individual level? And also trip level variations, as in things like eco-driving behavior, depending on routing, speed, things like that, we are going to see very different energy usage. Now I'm going to go over some of the assumptions that we've used in OpenPath over the years. So in 2014, OpenPath began as a PhD thesis project, and the footprint data was based on literature from the 2004-2006 area and a sensed mode from a very small list. And this was particular to the San Francisco Bay Area. This is how we got started. And then in 2019, an open source collaborator added some European sources, and users were able to choose in the app which source they wanted for their footprint estimations, their energy estimations. And then in 2020, in partnership with the Colorado Energy Office, we expanded the mode list that users are able to select the mode that they took from, including adding things like e-bike. And we updated all of our factors with data from the Transportation Energy Data Book, which is produced by Oak Ridge National Lab. In 2021, we added trip-specific mode labels to the in-app dashboard. So that's where you were seeing that color coding of, car versus shared car, those kinds of things, contributing to the energy usage of the user. And then in 2022, we added more labels for things like hybrid cars and e-cars to start to get down to that distinguishment between different types of the same mode. Here I'll walk through some of the progress we've made on these iterations. It's a lot of data on the screen. If you're interested in looking at the full detail of our calculation methods, everything is open source. But just looking at these first three columns in this table, you see the app method, then the dashboard method, then cheer. You can see that we're adding more and more mode options, introducing things like e-bike or bike share, hybrid cars. And then once we get down to cheer, we're starting to look up data for regional or time-specific variations. So looking at this call-out table for train values, we're looking at the progress of those emissions estimates, those energy estimates. And now with the cheer method, we're looking it up with NTD, National Transportation Database data, and getting the variance in regions to capture things like fleet composition and load factor that I was talking about a minute ago. All right, and then for cheer, I'll continue to get into some more detail here on the ways in which we were able to improve our energy and emissions factors, and then there'll be some limitations to that. This flowchart is just drawing the distinction between the dashboard method, which was close to what we saw in the literature, a little bit simpler, and then cheer, where we're now looking up data for transit modes. We're looking at NTD data, and for electric modes, we're looking at eGrid data from the EPA, and we're also paying close attention to the load factor, or the number of passengers that are on the car. And again, if you would like to look at these methods in detail, they are published in our GitHub repository. One of the other big improvements that we made with Cheer was the introduction of custom modes. So when we partner with a new organization or agency to collect data in a study that they're interested in and set up that hosting for them, we're asking them for a list of modes that they're interested in. People can add modes depending on their context. You're seeing two different lists of modes that are presented to users on the left and right here. Maybe they're adding something like motorcycle that's more popular in their region, and they're also able to adjust the energy and emissions factors that we're using. So maybe they have more accurate data for their region than we do, and they're able to provide that to us in their deployment, and we're able to customize it in that way. So talked about the NTD data. This is just visualizing some of that. That's where we're getting our transit efficiencies and load factors. The load factor is defined for us as the ratio of passenger miles reported to the number of vehicles miles that are reported for a given mode. Here we're looking at bus. So that's the data that you're seeing as average passengers on a bus in Colorado for each of the different urban areas highlighted. We're aggregating across fuels if needed for things, mixed fleets between electric and diesel, stuff like that. And then we're doing something similar with the eGrid data for electric modes. So here we're looking at those different eGrid regions, which they define, and the changes over time. It was very important to us that we be able to account for as much regional specificity as well as temporal specificity as we could. So here you're just seeing some of those big swings. I'll point out in the graph on the left, I know it was 6 years, but there is a change of 200 kilograms per megawatt hour of those emissions intensities in some regions. So now I'm going to take a moment to stack up the impact of switching between these calculation methods on some of the programs that have collected data using OpenPath. So the three that we're going to talk about showing here are CanBike Colorado, which you guessed it, took place in Colorado, Bull e-Bike, which took place in North Carolina, and then Mass CEC, which took place in Massachusetts. We've selected here the Dashboard 2020 method as the baseline because this sort of simple method is what was most present in the literature. So we're trying to stack up to sort of the field and what we're usually seeing. And as you can see, the difference can be quite large. And it also varies by region. The big difference you're seeing between App 2014 and Dashboard in Massachusetts is because of the large representation of transit in that data set and just how much of a difference having more accurate data can make to transit modes. This is highlighting changes over time. So for the Colorado data set, looking particularly here at bus and free shuttle, we see a drop from 2021 to 2022 in the estimated intensity of that mode, which could be due to things like number of passengers or fleet composition, as well as fuel generation. Maybe something changed in the grid. Those emissions intensities are changing over time. And here we're looking at cumulative differences in emissions estimates and energy impact, again, for the Colorado data set, and just noting here that the estimated cumulative totals are varying independently of one another between those two modes. And it can make a really big difference study-wide in how we are estimating those values. So it's very important to us that we're being careful and as accurate as possible. And then circling back to how I presented this as an individual transportation meter, here each bar is representing one user from the Colorado program, and it's color-coded by their the mode impact that's having on these differences. So it's a really big difference, particularly for bus users, again, with those changes in transit accuracy from things like occupancy level or fleet composition meant really big swings for those users. So if we're trying to present people with accurate information so that they can make their own decisions about things they might be trying to optimize for, having increased accuracy is very important. Next, I'll go over a few of the ways that we could improve. As you might guess, a lot of it has to do with getting additional data. So we'd love to be able to include marginal impacts for transit or replaced mode. I talked a lot about how there were some big swings in our transit data representation, but that is dividing sort of the energy impact of the bus by the estimated number of people on the bus, which isn't quite accurate to what is the impact of me getting on the bus if the bus is going anyways, kind of a thing. Accounting for micromobility fleet compositions, acoustic versus electric bikes, balancing activity in different cities is going to be different. Use of trajectories and temperature for trip level variations would be great. This is going to start to get at what I was talking about with those eco-driving behaviors, things like that, and additional mode specificity. So if we could have personal configuration of, not only is an electric car, a generic electric car, but it is, sort of my make and model electric car that I drive. If users are able to put that in, they would be able to access much more fine-grained estimations for their own behavior. There's also some limitations to the data that we were using. So there's some lags in the publication of data from the NTD, and we had a hard time finding any internationally available data. What we were able to find was behind a paywall and was also a couple of years old. We would love to get more time-specific data for electricity emissions. So things like, during the day, maybe more of the demand is met with solar or things like that. I know that I avoid using electricity during demand peaks because I'm charged more for it, things like that. The NTD data also reports pretty coarse vehicle types, and transit agencies are assigned to just a single urban area. So we had some problems where, the agency that operates in, say, Pueblo is reporting, but isn't reporting as for Pueblo. So we had some issues in accuracy there, and big e-grid regions and little accounting for community choice energy, things like co-ops is an example of that program in Ohio. And we also have pretty limited data for our ride-hail modes. We'd love to get more data partnerships there and able to increase our accuracy for things like Uber and Lyft. That was all of the information that I had for right now. I'd be happy to answer questions now or whenever is appropriate.
Thank you, Abby, for your great presentation. Any questions for Abby? I have two questions. One is about the app. So is it everybody can download the app and use it? What information does it provide for users that helps them reduce the emissions in their everyday life?
So yes, it is in the App Store. Anybody can download it. I believe we had some links in the chat of how you can get to that. You're able to join just what we call the open access study. So that's the one for anybody who's not being tagged to use the app as part of a specific program. And this travel diary and then the dashboard are the two sort of primary tools for the user to see their own travel.
Mm-hmm. I see. Another question. So I saw in your portal that you had electric cars as well. And you in your graphs you didn't have electric cars. You had only gas cars, but you talked about electric bikes. So what aspects of emissions did you consider for these electric cars and bikes?
For electric modes, we're looking at the emissions intensity of the grid in that region. I think that e-cars were not on some of our charts just because they weren't really highly represented in our studies. But yeah, we're looking at sort of an estimated energy use for those modes, and then we're multiplying that by the emissions intensity of the grid in that area.
Mm-hmm. Great. Any other questions? I don't see any questions in the chat box, so we can move to our next presenter. Thank you so much, Abby, for your presentation.
Thank you.
Silvano, are you ready to share your screen?
Yes, I'm ready.
Okay, I already introduced you. Feel free to start, share your screen and start your presentation. Thank you.
Do you see my screen?
Yes.
Okay. Hello, everyone, and thank you for joining our presentation at the Bridging Transportation Researchers Online Conference. My name is Silvano Bernabel. I'm presenting joint work with Felisa Vázquez-Abad from the Graduate Center at CUNY. Today, we're tackling a massive challenge: how to drastically accelerate discrete event simulations without sacrificing an ounce of statistical accuracy. We'll introduce a robust Markov renewal correction method, and by the end of our time today, we'll see how this applies not just in idealized sandboxes, but in messy, complex reality of finite constraints, the very environments we rely on for AI training. To really grasp the scale of the bottleneck, let's look at the New York City bike dataset. And we're talking about over 34.5 million trips across more than 2,000 stations. If you try to simulate this monolithically, the global priority queue quickly becomes a really massive CPU bottleneck. So sorting it scales logarithmically, and in our test, we took a 1-year simulation baseline, and to simulate it takes nearly 29 minutes. Now, imagine you're a transportation planner or an AI model that needs millions of iterations to learn dynamic routing. So nearly half an hour per run creates a severe decision impasse. So it's simply computationally infeasible. To contextualize where our work fits in, let's distinguish between two pillars of transportation research. Throughout this conference, you'll see fantastic empirical presentations. They're crucial for diagnosing the reality of our current networks based on historical data. But what happens when city planners or reinforcement learning models need to test a policy that doesn't exist yet? They can't just look at past logs, they have to rely on generative simulation to design the future. And building a simulation, however, is like building an aerodynamic wind tunnel. So before an engineer introduces complex turbulence, they first have to prove that the tunnel correctly simulates smooth air. That's exactly what our research focuses on, ensuring the underlying engine of our parallel simulation is mathematically flawless before we introduce the turbulence of real-world constraints. So how do we speed things up? The standard engineering fix is spatial partitioning. You divide the network into disjoint clusters, each with its own independent queue. And to keep things blistering fast, we completely cut inter-process communication during the run, and that gives you zero synchronization overhead. But here's the catch. This creates what we call the path suppression bias. And because roughly 50% of all trips cross cluster boundaries, those trips get prematurely truncated. And because of this loss in data, naive parallel estimators suffer a massive 38 to 42% estimation error. So you get speed, but your results become functionally useless. Let's visualize exactly why naive parallelization fails. Here we have a conceptual diagram of independent geographic clusters mapped over Manhattan. When we split the network and silence inter-process communication, any trip that crosses a boundary gets abruptly chopped off, as you can see here highlighted in red. This artificial truncation is what causes that systematic massive underestimation we just discussed. But here's the good news: with our Markov renewal correction, or MRC, mathematical bias correction steps in post-simulation. It effectively completes the expected path, perfectly stitching the statistical memory back together. To prove this method actually works, we set up a rigorous benchmark. First, we fed 1 full year of New York City bike data into a standard single-thread simulation. This gave us our unassailable ground truth baseline. Next, we took that exact same data, split the network into 18 independent clusters, and ran it in parallel across multiple CPU cores. The principal test of our benchmark is this: can these parallel clusters running completely isolated from one another mathematically reconstruct the exact global mean travel distance produced by the monolithic run? Our solution to the path suppression bias is the MRC. What makes it powerful is, first, it's strictly partition agnostic. It mathematically guarantees convergence regardless of how complex or messy your boundary lines are. Second, it's grounded in serious theoretical rigor. By treating the independent clusters as coupled renewal processes, it reconstructs the memory of those truncated paths post-execution. The result is it practically eliminates the bias, dropping that 41% naive estimation error down to less than 0.34%. The genius of MRC is that it achieves this without reintroducing any mid-simulation communication. During the parallel run, each cluster operates entirely independently, tracking just 4 lightweight local counters. We track the expected internal rewards, expected cycle duration, the boundary translation probabilities, and the expected boundary exit rewards. Once the simulation finishes, we take these local metrics and stitch them back together post hoc using a boundary matrix denoted as B. Here's a look at the end-to-end execution pipeline. We start with the raw event stream, passing it to our completely independent local clusters running in parallel. There's zero inter-process communication here. As they run, they simply collect those 4 local metrics. Finally, they pass these metrics to our post-hoc MRC solver. The solver does the heavy lifting, stitching the data together to compute the exact global mean. The theoretical engine behind this is the renewal reward representation. By solving for the unique stationary entry distribution alpha of our boundary matrix B, we can express the global mean exactly. Let's break this equation down. Here's our target global mean. It's driven by the expected internal reward of each cluster, divided by the expected cycle duration. We also factor in the expected exit reward and multiply it by the probability of transitioning between those specific clusters. And you might wonder, why do we have T sub k plus 1 in the denominator? It's a small but critical detail. The 1 is perfectly accounts for that final discrete boundary exit step in the renewal cycle. All of this builds to our core theoretical result, the theorem of asymptotic equivalence. We formally proved that as our sample size n approaches infinity, both the single cluster monolithic estimator and our MRC parallel estimator converge almost surely to the exact same global mean. The major takeaway here is that MRC is asymptotically exact. It completely frees you to choose whatever cluster count or partition topology best fits your hardware without ever worrying about structural bias. Now, even though MRC is partition agnostic, the way you cluster your network still impacts your sample efficiency. We first tested a standard approach, geographic k-means, which simply groups stations by Euclidean distance. Visually, it makes a lot of sense. It forms these tight, compact, geographically contiguous regions. But the downside is that human commuters don't care about our artificial borders. This approach yields extremely high intercluster boundary traffic, meaning we suffer a lot of path truncation that the MRC has to work hard to correct. To minimize that boundary traffic, we compared geographic grouping against a Kemeny-based clustering approach. This method analyzes the sensitivity of the network's mixing time, pruning weak connections to isolate strongly connected components, and then consolidates them using cosine similarity. This produces non-contiguous fragmented geographic footprints. The trade-off is that it preserves stochasticity, connectivity, retaining trip flow internally, and significantly reducing those boundary crossings. When we run the numbers, the empirical results speak for themselves. Our single cluster ground truth for average trip length is about 2.47 kilometers. If you use naive estimators without our correction, they severely underestimate the distance, coming in at around 1.43 kilometers. That's nearly a 42% error rate. But our MRC successfully recovers the ground truth distance within a 95% confidence interval, limiting the error rate to less than 0.34% across both spatial clustering models. We effectively eliminate the bias. And what about performance? In terms of true wall clock acceleration, our runtime plummeted from nearly 29 minutes down to just 37 seconds on 18 clusters. That is a staggering 46.3x speed up. You might notice this is scaling is super linear. It's because we are splitting the queues and we drastically reduce the heap sorting depth. Even more importantly, these much smaller subheaps now fit entirely inside the ultra-fast L2 and L3 CPU caches. So we eliminate those slow DRAM memory latency stalls entirely. At this point, you might be asking, why did we benchmark this in an idealized sandbox with infinite bikes and docks? After all, real transportation networks are defined by their constraints. It's a great question. The answer is that that path suppression bias is a foundational mathematical flaw in spatial partitioning. If a parallelization method cannot perfectly preserve the unbiased routing flow of an unconstrained baseline, it will completely collapse once you inject the chaos of finite capacities. By isolating the bias in this sandbox, we proved that the MRC routing engine is mathematically bulletproof. Only then can we confidently layer on the complex operational noise of the real world. So what happens when we introduce real-world constraints? The beauty of the MRC framework is that our local clusters remain fully functional discrete event simulators. If a station in a cluster hits maximum capacity or runs completely out of bikes, that logic is handled natively right there within that independent run. Planners can model local rebalancing trucks or set up dynamic threshold alerts entirely out of the box. The MRC doesn't interfere with intra-cluster logic. It only steps in at the end of the simulation to govern the statistical stitching across the boundaries. When it comes to modeling cross-cluster dependency, the MRC framework acts as the engine for a fast, iterative relaxation loop. You simply run the high-speed parallel clusters, adjust the boundary matrix B based on the new flow, and rerun until equilibrium is reached. Ultimately, this is why MRC is a game changer for this research community. It breaks the computational impasse for massive synthetic data generation. For those of you building reinforcement learning models, MRC gives you exactly what you need: a high-speed, perfectly unbiased simulation environment capable of training dynamic routing agents over millions of iterations. Before we wrap up, I want to transparently address the current limitations of our model. First, we currently assume the origin-destination demand matrix P remains constant. We know urban mobility heavily fluctuates during AM and PM rush hours, so a static MRC can lead to lagged estimates. We plan to fix this in future work using a piecewise stationary approach. Second, we assume trips are memoryless, which might miss longer complex routing dependencies. Finally, as discussed, our benchmark assumes infinite capacity. Our next research step is to incorporate finite docks without breaking our independent clusters, likely by pre-computing the network's macroscopic equilibrium before the simulation kicks off. In conclusion, the Markov renewal correction framework fundamentally solves the parallelization bottleneck for large-scale discrete event simulations. By achieving a superlinear 46.3x speedup while simultaneously dropping estimation error to practically zero, we provide both the computational scalability you need and the mathematical exactness you must have. Thank you so much for your time, and I'd be happy to take any questions.
Thank you so much, Silvano. Any questions? Very interesting presentation. So we have one question. They're asking, could you please return to slide 13? They have a question on slide 13. Michael, you can unmute yourself and ask your question.
Yes.
Okay, not allowed. I didn't know that. So please ask your questions in the chat box. And Silvano, could you please answer the question after your presentation?
Mm-hmm.
I have a question. So is this approach applicable to discrete choice models like destination choice model and similar problems?
I'm not familiar with
the discrete
that type of.
We have different,
Yeah, I'm not familiar with that type of problem, but
destination.
I think mathematically it wouldn't matter. Whatever you're modeling.
I see. So, what are the inputs that the user should assign? So, should we assign different clusters to different threads, or it will be automatically assigned depending on the number of threads on the computer?
You can assign whatever number of clusters you want. You're free to do anything. Yes.
And it's not limited to the number of threads?
No.
Okay. So we have a question from Michael. Why is the Qianwen error slightly higher?
Which is higher? What number? The error?
The error, yes.
Because the Qianwen is higher because it's preserving more I know that it's preserving more the clusters of the stations, so it's eliminating the connections that are weak, and because of that, the MRC has to. It takes longer for it to accumulate to equilibrium, so therefore, by the time simulation finishes, you have a little bit more error remaining. So if you were to run it longer, then it will be even closer to zero.
I see.
Mm-hmm.
Okay. Any other questions, Silvano? If not, we will move to, thank you so much, Silvano, for your presentation. We'll move to our next presentation from Daniel Udekwe. Daniel could not join us today, so we have to play his recorded presentation. Arna, could you please start the presentation? Thank you so much.
Good morning, everyone. My name is Daniel Udekwe, and I'm a PhD student at Florida State University. Today, I'll be presenting our work on behavior-aware traffic prediction for hurricane evacuations using adversarial inverse reinforcement learning combined with deep neural networks. I'd like to acknowledge my advisor, Dr. Guo, for her guidance and support on this work. Here's a roadmap for today's talk. I'll start with why evacuation traffic is such a hard forecasting problem, and then I'll walk through our research objective, our methodology, which combines a behavioral model with two prediction models, And finally, our results across short-term and long-term predictions and transfer learning experiments. Now, hurricane evacuations push traffic forecasting to its limits. Large populations have to relocate within a narrow time window under conditions that are changing rapidly and unpredictably. Getting this forecast right matters because it's what lets agencies stage evacuations, provide route guidance, and run contraflow operations. You can actually see that disruption right here on a real road segment along I-10 during Hurricane Sally. The blue line is the observed hurricane impacted speed. The red line is the typical historical average for that same stretch of road. And so you can notice how erratic the observed speed become and how far they drift from the historical pattern, especially right around the time of landfall. So that's the kind of noisy, non-stationary signal that our models have to work with, and it's a big part of why the problem is so hard. And now, historically, there have been two ways to approach this. We have model-based methods which explicitly represent evacuee decisions, but they require heavy calibrations and don't adapt well to fast-changing evacuation dynamics. That's the line of work for these authors that you can see shown here. And on the other hand, we have the data-driven methods which learn patterns directly from historical traffic, as in the works that are represented here. But the problem with these methods is that they treat behavior as just noise in the data rather than modeling it as a decision process. So that's the gap that we are targeting. Neither paradigm explicitly models why evacuees choose their routes and departure times. They only capture what the traffic looks like around the fact. So our objective is to develop hurricane evacuation traffic prediction models that explicitly incorporate human behavioral dynamics using adversarial inverse reinforcement learning to improve accuracy under these complex, rapidly changing conditions. Our methodology is a three-stage pipeline. First, pre-processing and alignment. We don't just look at evacuation traffic in isolation. We pull in three data sets on purpose: the actual evacuation period data from the affected region, a prior year baseline from that same region, and a controlled data set from a region the hurricane didn't affect. And the reason is that raw evacuation traffic on its own is a tangled signal. Part of it is just normal seasonal and day of week variation. So part of it might reflect things happening elsewhere that year, and only part of it is actually caused by the hurricane. So the prior year baseline lets us subtract out what's normal for that road at that time of the year, and the unaffected region lets us rule out anything that isn't specific to the hurricane. So once we align all three to a common road segments and time beans, what's left is a much cleaner signal of evacuation-induced disruption. Second, we have the feature construction, where we estimate that baseline and adjust for temporal patterns to isolate the evacuation-induced deviation, and then run our adversarial inverse reinforcement learning model to extract two behavior-aware features, which are route choice, entropy, and maximum transition probability. Third is the model training, where we use a transfer learning framework that pre-trains on routine non-evacuation traffic dynamics, then fine-tunes on evacuation data itself. This feeds two downstream outputs. We have a short-term speed forecasting model using an LSTM, and a long-term congestion classification using an MLP. So let's dig into that behavioral model because it's the core contribution of this work. We frame route choice as a Markov decision process. At each point in the trip, the driver is in some state defined by their current segment, local speed conditions, and how close they are to landfall. And they choose an action, which segments to move next. So we train this using adversarial inverse reinforcement learning, or AIRL as it's called. A reward network and a policy network are trained together adversarially against a discriminator that is trying to tell real observed trajectories apart from the model's generated ones. overtraining, the model's policy converges towards the real behavior. And from this learned policy, we extract our two behavior-aware features. What do these two features actually capture? Route choice entropy measures decision uncertainty. When it's high, evacuees are hedging across several similarly attractive routes. That's a leading indicator of instability, and it's something a traffic management center could act on before congestion even shows up in the speed data, for example, by adjusting variable message signs. Maximum transition probability is the opposite signal. When it rises, evacuees are converging onto a single dominant corridor, a kind of funneling effect as landfall approaches. So that flags exactly which corridor needs priority for example, contraflow or capacity management. And both of these signals compute in near real time from streaming probe vehicle data. So they are not just model inputs, they are potential live decision support signals. For short-term prediction, we use an LSTM. It takes a sequence of traffic features such as speed, trip counts, and temporal features like hour of day and our behavior-aware features, and encodes them into a hidden representation. This gets passed through fully connected layers to forecast speed at 4 horizons. We're using 15 minutes, 30 minutes, 60, and 90 minutes ahead, with a separate model trained for each horizon. For the longer time scale, we classify congestion over 6-hour windows using an MLP. We compute a speed performance index, which is essentially observed speed relative to the historical average. And then we bucket that into 3 classes of no congestion, light congestion, and heavy congestion. The same aggregated traffic, temporal, and behavior-aware features are fed into this classifier. For the case study, we validated this on Escambia County, Florida, during Hurricane Sally in 2020. Our data comes from INRIC's large-scale probe vehicle trajectories, covering a 3-month window around the storm, and we evaluate it at 2 granularities across 4 representative corridors, spanning urban, suburban, and rural conditions. Now to the results, starting with the short-term speed prediction. We see that adding our ARRL-derived behavioral features cuts prediction error at every single forecast horizon, and these are statistically significant improvements with p less than 0.001 throughout. So we see a reduction of about half kilometer per hour in MAE, mean absolute error, at the 15 minutes horizon, growing to almost a full kilometer per hour reduction at 90 minutes. And when we ablate the 2 features individually, entropy alone or maximum probability alone, each recovers only about 2/3 of the full gain. So the 2 features are capturing complementary information, not a redundant signal. The same behavioral features also sharpen our long-term congestion classification. Across our classifier, the MLP classifier, and 2 others that we included, SVM and KNN, we can see that adding ARRL features improve accuracy by about 1.4 to 1.6 percentage points, and macro F1 by roughly 0.05, with McNemar's test confirming significance for every classifier. So this matters more than it might sound, because our congestion classes are heavily imbalanced, with about 96% of observations belonging to the no congestion class. So this macro F1 gain reflects real improvement at catching light and heavy congestion cases, exactly the cases that matter operationally. The transfer learning results actually surprised us. We expected pre-training on routine non-evacuation traffic and then fine-tuning on evacuation data would help, but it mostly didn't. So pre-train only with no fine-tuning at all fails badly, with a mean absolute error over 21 kilometers per hour at every horizon, which tells us that there's a real domain shift between routine and evacuation traffic. And even with fine-tuning, we are statistically worse than training from scratch at the 30 and 60-minute horizons. But, and this is the key finding, when we combine transfer learning with our AIRL behavioral features, we get our single best results across the whole study, which is 7.31 kilometers per hour MAE at the 15-minute horizon. So our transfer learning alone isn't reliable, but it pairs very well with behavior-aware features. Before I wrap up, I want to be upfront about 4 things we haven't shown yet. First, this hurricane happened during COVID-19, and that shapes our data in a way I should flag. Hurricane Sally made landfall in September 2020, and Florida's emergency management guidance at that time actively discouraged congregate sheltering, things like public schools, in favor of non-congregate sheltering, mainly hotels, to limit disease transmission. And that matters for us because school-based shelters are usually spread fairly evenly across neighborhoods, but hotels are concentrated in specific areas. In Escambia County, I think that's mainly around Pensacola and the I-10 corridor. So some of the destination and route choices that we're capturing in this data set may reflect that pandemic-era sheltering policy, which pulls evacuees towards those hotel-based areas rather than route and timing behavior that you would see in a typical non-pandemic evacuation. So with a single event like this, we can't fully separate that pandemic effect from evacuation behavior that would generalize to other storms. Secondly, we don't yet have ground truth behavioral validation. We haven't checked our AIRL policy against documented, publicly reported route usage for this region, and we haven't validated it against household surveys or stated preference data, which is really usually the gold standard for confirming that the model has a learned genuine decision-making behavior rather than just a pattern that happens to fit the data. And third, our current formulation treats each route's features largely independently, but we know that in reality, evacuation traffic on one corridor affects conditions on neighboring or downstream corridors. So congestion propagates across the network, and we are not capturing that network-wide propagation yet. Finally, this is just one hurricane and in one county. So cross-event and cross-region transferability, whether this same framework holds up for a different storm or for a different part of the country, is still an open question. So to conclude, modeling why evacuees choose their routes actually improves the forecast on how traffic will behave. Concretely, our AIRL derived behavioral features significantly reduce short-term prediction error at every horizon, and they significantly improve long-term congestion classification across all 3 classifiers we tested. Transfer learning from routine traffic alone isn't reliable, but pairs well with these behavioral features, and entropy and max transition probability can double as real-time, human interpretable decision support signals for emergency managers, not just inputs buried inside a model. These are the key references for today's presentation. I'm happy to share the full list and the paper afterwards. Now, for the sake of completeness, I've included a few additional slides that support what I've just walked through. I won't go through each of these slides in detail because they do not contribute much to the discussion, but these first 2 slides are the same multi-horizon forecasting results that are broken out route by route. So here we have Route A, Route B, Route C, and Route D. So you can see how the AIRL enhanced predictions track actual speed on each individual corridor. Then we also have the observed versus predicted congestion maps that I mentioned earlier, but these are broken out across 4 6-hour windows which we modeled. So first of all, we have midnight to 6 a.m. We have 6 a.m. to 12 p.m. We have 12 p.m. to 6 p.m. And then we have 6 p.m. to 12 a.m. So here you can simply see side by side how closely the predicted congestion patterns track what was actually observed across each period of the day. Finally, thank you for your attention. I'll be glad to take any questions, and my contact information is right here if you need to follow up afterwards.
Okay, great. So Daniel is not here. If you have any questions, please feel free to contact him by email. Without further ado, we will move to our next presentation. Our next presenter is Mohammed Nafees Fuad Rafi, who is a PhD candidate in transportation systems at the University of Central Florida. His research focuses on applying AI and learning algorithms to transportation systems, with particular emphasis on traffic prediction and evacuation management during natural disasters. His presentation today is about reinforcement learning guide dynamic multigraph fusion for evacuation traffic prediction. Nafees, please feel free to share your screen and start your presentation.
Thank you so much, Dr. Fatemeh, for the introduction. Let me share my screen first. Can you see my screen?
Yes, we can see that.
Okay. So, hello everyone. Welcome to my presentation on reinforcement learning guided dynamic multigraph fusion for evacuation traffic prediction. So this research is part of one of my PhD work on evacuation traffic prediction. So without further ado, let's just dive in. So here I will talk about a little about the motivation behind this research. As the earlier presentation was discussing, predicting evacuation traffic is so much harder than predicting regular traffic, because evacuation traffic doesn't usually show the regular morning peak, evening peak, or regular on-off peak periods that regular traffic does. So capturing those patterns from a little amount of evacuation traffic data is so much harder. So what we try to do is we try to look up the literature to see what kind of models that we have. And generally, we found that there are graph neural network models that are usually used to predict evacuation traffic flow. But the problem with graph neural network models is, as the earlier presentation was discussing also, they are usually trained on regular traffic conditions. But evacuation traffic patterns is much different than regular traffic. And another limitations that we found in the existing literature is the existing graph neural network models are static graph models, which is the underlying network that they have built the model on. They assume that the network remains static. But in reality, if we see in the figure at the right, we see that the traffic detectors that are giving the network-wide traffic data to us are highly dynamic, and they can regularly go online or offline depending on different situations. Maybe there is some power outage, there is some maintenance, there is some communication errors, and also there are also some new detectors always keep being installed, or previous detectors go out of order, or some kind of issues. So the underlying network that we have for graph neural networks based on this detector-based traffic data, they are always changing. And when it approaches the evacuation timeline, we see that due to power outage or for some other reasons, the network-wide detector availability or data availability, it drops too low. And also for other time, here, as you were seeing, the traffic detector availability just before the Hurricane Milton during the peak two peak evacuation days, October 7 and 8, 2024, the number of active detectors in the networks, it keeps always changing. So if we ignore this evolving detector network or evolving network topology in our prediction model, that may hamper the network-wide generalization or prediction accuracy of our graph neural network model for traffic prediction. And also, the previous models were for regular traffic conditions. So if we want to predict evacuation traffic, we thought that it would be much better to train a model that is only trained on previous hurricanes evacuations traffic data. So that was another motivation of ours. So dynamic graph learning it can solve some part of this problem, which accounts for the dynamic detector topology, but existing dynamic graph learning models that we have in the literature, they are only distance-based for capturing the network's relationships. But distance is not a complete information. Travel time can give us a more complete information of the network congestion and dynamics itself. So we thought that if we can fuse the distance-based and travel time-based graph and create a dynamic multi-graph fusion model, that can give us a better prediction accuracy. And also another problem is the existing graph learning based models, they work like a black box. We actually don't know what individuals features contribution is toward making a better prediction. So we try to solve that problems also. So with keeping those in mind, we try to develop an attention-based dynamic multi-graph fusion module that fuses both distance and travel time. And we also introduced a reinforcement learning-based intelligent feature selection and ranking method that learns to perform intelligent feature masking based on its contextual importance for making the prediction better. And integrating these two portions, like the dynamic multigraph fusion and the reinforcement learning-based intelligent feature selection and ranking, we created a novel reinforcement learning guided dynamic multigraph fusion architecture for network-wide evacuation traffic prediction for future hurricanes. So in order to create this model, we first collected traffic data for 12 historical hurricanes that have hit Florida. Florida is a very hurricane-prone region. So without the previous year, 2025, almost in every year we had at least one hurricane, and in some years in 2024 we had 3 hurricanes. So for each hurricanes we collected 10 days of data, including the landfall date as the last day, and we collected 10 days of data before the landfall day for each of the hurricanes. Although the evacuation time may not last for 10 days, but we wanted the model to have some regular period traffic data as well, so that the model can learn how traffic propagates and everything. We also collected incident-related data and merged it with the detector information. And to give our model some evacuation-related context as well, we collected evacuation data from Florida Division of Emergency Management. So here, at the figure in the right, we are showing the 10 hurricanes pathway, and we collected the network-wide traffic data for 5 major highway corridors of Florida, which is I-4, I-10, I-75, I-95, and Florida Turnpike. These are the model features that we have considered, which include both traffic features, and also we have considered incident-related features, and also there are some evacuation-related features as well, like among those 10 days, which are the evacuation days, and also to make the model more dynamic, we try to include features like how many times or how many hours are left before the landfall. And also for each counties, the evacuation order timing was different. So we wanted to capture like what amount of time has been elapsed after the evacuation order has been placed county-wise. So these type of features helped the model to have better context about what amount of traffic gonna hit the road in next couple of hours. this is the dynamic multigraph fusion module that we tried to develop. The first portion is the dynamic graph construction, which is basically based on one of our previous work. Dynamic graph construction basically creates a dynamic graph at every time step from a detector master graph, which includes all the possible detectors that a network might have. And once we have the master graph, uh, it just figures out at each time step that if that one detector is giving data or not. Let's say here, the detector, let's say at any given time step t, the detector 8 and 9 may not be available. So what dynamic graph construction does is it reroutes the graph from 3882 to only 32, and we then create this new edge 32 and assign an edge weight which is basically the sum of the edge weight of 38 and 82. So in this way we create the dynamic graph, network-wide dynamic graph at each time step, and we do this for both distance-based graph and both travel time-based graph. So once we have these two graph information available, we then pass it through a graph convolutional layer. And once we have the GCN hidden state out of the graph convolutional layer, then we do a dynamic multigraph fusion based on an attention mechanism. The attention score basically weighs the importance between the distance-based graph and the travel time-based graph. And based on this attention weight, and based on this importance, a new fused embeddings is created, which then pass through the LSTM layer, which tries to capture the temporal dependencies of the traffic data, and then we pass it through a final linear layer to do the prediction. And to give a little more context, this is a real-time model, and it goes on like a sequential basis, and at every time step we use past 6 hours of data, including the current time step, to predict for next 6 hours, and it goes on like a rolling basis. So that's where the LSTM plays a role. And in order to have the reinforcement learning, what we do is we treat the whole prediction mechanism as a reinforcement learning environment. We integrate it in a reinforcement learning environment where this prediction mechanism interacts with a double deep queue network agent. And what that agent does is at every training step, it masks one individual feature. And by masking that feature, it runs through the whole DMF module, runs the prediction, and get the prediction result, and it tracks down if the result is accurate or not, or if not accurate, how much error in that result has. So based on that error, it just penalizes the agent. So based on this mechanism, it goes on like step by step of every training iteration. And it does do the masking on a random basis, but once it tries to gather some experience, it tries to store it in the replay buffer memory. And with time, with every training step, the model, the DDQ1 agent, it learns which feature is most important based on this intrusive masking mechanism. So the feature that is masked less amount of time would be the feature that is most important. So that's how it works. So just to show some of the results that we got out of this work. So here at the left, we are showing the prediction performance of the RLDMF model for next 6-hour prediction horizon during the evacuation period of Hurricane Milton, which is October 7 to October 8. So within those peak 2 days, these are the results that we got. We see that the 1 hour prediction RMSE is much more lower, but as the prediction horizon is increasing, the prediction performance is getting poor, and which is very common for any time series model involved. And also the rest of the metrics, MAE, MAP, and R squared, they are also devaluating as the prediction horizon is increasing. We also compared our model with some state-of-the-art traffic prediction models that we have. The figures at the right shows that we got an overall RMSE and MAE much lower than all rest other models for those 2 days of evacuation period. And also the top two figures are showing that the hourly predicted values also has less errors for our model compared to all rest other traffic prediction models. These are the actual versus predicted flow that we have. As we're seeing, as the prediction horizon is getting larger, the plot is become much and much dispersed, meaning that the error is increasing, but still it is not that out of order. This figure shows the average actual versus predicted flow for the next 6-hour horizon for Hurricane Milton. We see that the blue dots and the orange dots, they mostly coincides for shorter horizons, but in the longer horizons, we can still see some of the blue dots behind because they're the values kind of disperse from the actual one. We also tested our model to predict for a different hurricane, which is Hurricane Ian. And for that one, we trained our model using all hurricanes data that made landfall before Ian, so that we can keep the modeling steps logical. And we then tested in for the 2 days evacuation period of Ian. So here we can see that the model performed slightly better compared to Hurricane Milton, as we can see the lower error overall for Hurricane Ian. It can be attributed by the number of population that were under the evacuation order during Hurricane Ian. If you see the literature and in the news and also in our model, we found that around 2.5 million people were under evacuation order during Milton compared to nearly 5 million people in Milton. So Milton's evacuation was much more larger and vast compared to Hurricane Ian. And also the mean flow, it is also reflected in the mean flow. Like the mean flow of Ian is much smaller compared to Hurricane Milton. So that's why we get a better result for Hurricane Ian. This is a corridor-specific evacuation matrix. We saw that for both Hurricane Milton and Hurricane Ian, it passed through the western coast region of Florida. So the two major corridors that were under evacuation order were I-4 and I-75. So we tried to see what our model performs in those two corridors, and we saw that the performance was slightly degraded compared to the overall network-wide performance that we got, but still the performance is not that bad compared to what other models have performed in those two corridors. These are the changes in evaluation metrics with the input horizons is increasing. As the input horizons were increasing, we saw that if we use more hours of data to train our model, we are getting much and much better results. As we can see, if we just use the last 1 hour of data, our RMSE is around from 600 to 650 compared to what we got in the last, if we use last 6 previous hours of traffic data to predict next 6 hours of flow. There's some little ablation experiments that we run. It just shows that each individual portion of the whole RLDMF model is essential to make the prediction performance much better. We isolated the reinforcement learning distance-based graph. We also isolated the travel time-based graph performance, and we also isolated the reinforcement learning, and we found that the whole each portion is much and much important to make the prediction performance better. I don't know if you guys are able to see this traffic flow here. We prepared a congestion diagram out of the RLDMF framework, which just shows how the traffic is propagating network-wide through the whole Florida highway network. And also, as I have told you, the model also gives us the feature ranking in terms of intrinsic feature masking frequency. So here we can see that to predict the next 6 hours of traffic volume, the most important feature is the previous 6 hours. So volume was the most important features, followed by the previous daily mean, previous period of mean, and standard deviation. And all volume related statistics were much more important to predict next 6 hours of traffic flow. We also compared our feature importance mechanism with some of the traditional feature importance mechanism that we have in the literature, like Schwab or permutation feature importance. And we found that among all these steps, the top 3 features were very much aligned in all these 3 mechanisms. And for the top 20 features, we found that it varied from 60% to 80% alignment among all the top features that are making the predictions, which just shows that the reinforcement learning based feature selection or feature importance mechanism is very much aligned with the traditional SHAP or PFI mechanism that we have, except for the fact that the SHAP and PFI, they do not improve the model performance itself. They just act as a mechanism that we can use to make the feature engineering much more better, but it will require more and more training iterations to run multiple models with new features and everything. But our reinforcement learning step mechanism that solves this problem by doing it intrinsically and inside the model itself. It just reduces the training steps. So to conclude, we found that the proposed RLDM framework that we have, it enhances the predictive accuracy, and it also helps to solve some part of the model black box problem. It improves the interpretability, and we also found that it has improved the model performance compared to other state-of-the-art models for evacuation context. And our ablation experiments also showed that integrating DMF and RLIFSR module are both important for the whole RLDMA framework to work better. And the framework is interpretable and generalized network-wide. It can help to predict traffic for any future hurricanes of Florida. Thank you.
Great presentation, Nafees. Thank you so much. So we have one question in the chat box. Shankari mentioned that better results with more data makes them worry about overfitting. Do you have any explanation about that?
Yeah, so overfitting is always a concern for deep neural networks model. But by the way, for our case, we didn't use any of the regular period data like the rest of the works did. We found some literature that have used last 3 months of regular period traffic data, which is much more larger than the amount of data that we have used. For our case, we have used 10 days of data for each of the hurricanes included. So in terms of the overfitting, as we are saying, we tested it with the number of input horizons and the amount of data that we used. We had another previous research on that, which showed the amount of data required to make the model performance better. And we found that almost 5 to 6 hurricanes data would be enough to make the model results acceptable, model performance acceptable. So this research is just an extension of that one. So that's why I couldn't show you the amount of data requirements the influence of the data requirements on the model performance. But yeah, so we can say that a previous 6 hurricanes, 10 days data, or this amount of data might be enough for making the predictions better. If we don't have the much amount of data.
Great. So I have another question. You mentioned something about detectors that had missing data, and I guess you used an data imputation to fill out the missing data. Is that right?
Yeah. So some of the detectors did not have all data for all input horizons. So what we had to do is we have adapted an imputation technique to fill out those data. But the thing is, the model was dynamic in terms of detector availability. Although some detectors do not have data in any, if any detector do not have data at all, that detector was considered inactive at that time step. And we also had some thresholds to see, like, if the detector data that it is reporting, if that data makes sense or not. Like in overall sense, if that data, let's say it is giving zero volume, or it is giving some of the volumes that doesn't make any sense. So we just fix those datas with our imputation techniques.
Okay, great. You perfectly answered my question. So if there isn't any other question, we'll move to our next presenter. Thank you so much, Nafees, for your great presentation.
Thank you, Dr. Fatemeh.
So our next presenter is Yuyan Pan. She's a postdoctoral researcher at the Florida A&M University and Florida State University. Her research interests include traffic operations and management, intelligent transportation systems, transportation resilience, and data-driven transportation analysis. Today, she's going to present her work on quantifying AI gain in fundamental diagram-based traffic prediction. Yuyan, please feel free to share your screen and start your presentation.
Okay, thank you, Mahada. Can you hear me?
Yes, we can.
Okay, let me share my screen.
We can see your screen, yes.
Okay, good. Thank you. Good afternoon, everyone. I'm Yuyan Pan, and I'm come from Florida State University. Today, I will present our paper on how fundamental diagram structure and AI model capacity affect AI gain in traffic estimation and prediction. First, I want to briefly introduce the traffic estimate problem. Traffic state estimation aim to estimate traffic variable such as the traffic flow density and speed using particle observed traffic data. So, as shown in the figure, we use limited observation data to estimate the complete the time space on traffic data. And traditionally, traffic state estimation method can be divided into two groups. One is model-driven and another is data-driven method. And the fundamental diagram are physically interpreted and based on traffic flow theory, but their flexibility is limited. So AI model can also complex the nonlinear pattern, but however, the AI model may lack physical consistency. So both method, model-driven and data-driven, they have their own advantage and limitation. And so to combine their advantages, so recently people research always use the physical guide learning method has become an important research direction. However, many research assume that adding physical knowledge will always improve AI performance. And we believe this is not always the case. And the effectiveness may depend on both the complex of the physical model and the capacity of the AI model. So therefore, our main question is what combination of physical structure and AI capacity can provide the best performance? And we proposed then we proposed the physical guide FDA hybrid modeling framework. First, we calibrated the different fundamental diagram model to using the observed traffic data. And second, we use AI model I introduced to learn the remaining residual patterns. And finally, we want to evaluate the prediction performance and examine the interaction between the FD complex and the AI capacity. In this study, we consider 10 fundamental diagram model from there are different structure forms from the very simple model such as the green shared model and to the more complex model or recently, for example, the S3 model. We test those different model and this allowed us to significantly systematically investigate the effect of the physical model complex because they have different shape and different parameter. And so for the AI components, we select 5 models with different level of learning capacity. It includes linear regression, SG model, and MLP, and LSTM, and transformer. Those models range from the simpler linear learning to more complex nonlinear model. So, and here we show the detailed configuration of the 5 AI model. And the important point is that we maintain identical AI configurations across different FD variables. And in this way, we can better isolate the effect of FD structure and the AI capacity. This slides we summarize our end-to-end methodology, and we start with the real-world observed traffic data, include flow, speed, and occupancy density, and then we calibrate the FD model and obtain their prediction and residual. And then we use the AI model, learn those residual pattern, and improve the final prediction. So finally, we evaluate the performance and analysis by various physical trade-off. So more specifically, we classify we select the 10 FD model into low, medium, and high structure complexity. And we also consider 5 AI model with increasing learning capacity from every FD and AI combination. We use identity called training setting, and this experimental design allow us to focus on the interaction between the physical structure and the AI capacity. So next, I want to introduce an important concept in our this study. We call it AI game. What is AI gain? AI gain, it measure how much prediction error is reduced after ending AI model to the physical model. So it is defined as the error of the FD only model minus the error of the FD plus AI model. It means a hybrid model. So a positive AI gain, it means that AI improves the prediction. And a larger AI gain, it means a greater, or more bigger, or more good improvement. So we expect the AI gain can to depend on both FD complexity and AI model capacity. The next part is our data. For our experiment, we first select representative sensor from several major physical freeway corridor in the Los Angeles, and those select sensor cover different freeway and direction and lane configurations, and it can provide them diverse traffic condition for model evacuation. And then we extend the analysis to the Los Angeles freeway network. So this data set, it contains 150 mainline sensor across 5 major freeway corridor. It include I-5, I-10, I-110 and I-210 and I-405 corridor. These 5 main corridor in the Los Angeles. And this data set, we obtain from the PAMS, and it is 5 minutes resolution, and it covers all year in 2018. So the main variable, it includes the flow speed occupancy. We download this is observed data. And now I want to move to the result. First, we calibrate all the previous with select 10 fundamental diagram model to the observed traffic data with the least square method. So this figure, this slide, it shows the fitted flow density and speed flow and speed density relationship. We can see that different FD model provide different level of flexible in respond the observed traffic pattern. And here I summarize the calibration result, and I use the S3 model as an example to show the calibrate parameter. It includes the free flow speed. It includes the free flow speed. It includes the free flow speed, critical speed, critical density, and capacity. And we also observed significant data dispense, especially under congestion conditions. And even the flexible FD model can't fully capture this person with the single determination relationship. Therefore, this is still have some room for the AI-based correction. So next, we use this compares the overall fitting performance of the 10 FD model. So we can see the flexible nonlinear model generally performs better. And in particular, the 5PL ranks the first, and then is the S3 model with a average R square is about 0.8 3, and lower complexity model generally show larger error, and even the best FD model still leave some systematic residual errors. So this can motivate us to the next AI argumentation test. And next, so we examine the performance improve after ending the AI model. The main finding is that the AI argumentation improves prediction accuracy across all FD structures, and however, the amount of improvement is different. So low complexity FD model generally obtain larger AI gain because they leave more residual pattern for the AI to learn. And in construct, the high complex FD model already provides stronger baseline performance, so their additional AI gain is smaller. This shows that AI effectiveness strongly depend on FD structure complexity. And we also investigate whether a more complex AI model always provide better performance. It is interesting. The answer is no, and MLP consistently achieve the best performance across different FD structure. And linear regression model is too simple, so to capture the complex residual pattern. However, higher capacity model such as LSTM and transformer, they do not outperform than the MLP. So this suggests that moderate model capacity provide a better balance between the flexible and generalization. These slides show our main finding, and for the simple FD model generally achieve larger AI gain, while the complex FD model shows smaller improvement, and also more complex AI model do not always perform better. Yes, and therefore the key finding is that the right combination of the FD complexity model and AI gain. And finally, the conclusion, I want to like to summarize our main conclusion. First, the AI argumentation improve prediction and estimation performance across different FD structures. Second, more simpler FD model generalize achieve larger AI gain. And third, more complex AI does not always perform better. So overall, the key finding is that to find the right balance between the FD complex and AI capacity. Finally, I would like to thank all of my collaborators for this their contribution to this research. My advisor, the corresponding author, Dr. Qianwen from Florida State University, and Dr. Xianbiao Hu from Penn State University, and Dr. Su Hongzhou from Arizona State University. We also want to thank acknowledge the funding support for our research. We sincerely appreciate the support from NSF project and the USDOT project. This is the end of my presentation. Thank you for your attention. Thank you, Fatemeh.
Yes, thank you for your presentation. We have two questions in the chat box. The first question is asking, can you clarify what occupancy means in the data set, vehicle occupancy? How is that determined from freeway sensors?
Yeah, and this is a good question. Yes, this occupation, it means yes, the vehicle occupation. We actually we download this data is from the PAMS because you know the traffic density is difficult to obtain. So they use the occupation, they use the time difference between the first the leading car and the following car and calculate the occupancy. So it is basically we this occupancy parameter is we obtain from the original observed data, downloaded data. Thank you. And
with your answer to Shankari, I think occupancy, what they mean here is the amount of time that vehicles occupy each sensor. So
yes,
the information that, you know, they use, I guess, for traffic flow.
Yes.
Don't mean vehicle occupancy here, yes.
Yes, correct. Thank you.
Yeah. So the second question is, I'm curious if you have tried data-driven AI to confirm that physics-guided AI is better.
Yes. This is a very good question. In this research, I just test the physical guide with no physical guide, and I also forward to research to next step is to research the fully data driven. But the motivation about this research is if the fully data driven AI, it must have more good performance, but it lack parameter explanation. You know, it lack the physical part. So yes, maybe this will be our part of our data set, but we want to focus the physical guide and the hybrid model. Yeah, I will try to test this. Thank you, Hasan, for your question.
Great. Any other questions from you, Jan? No other question. Thank you so much, everyone, for your presentations. We missed one presentation today, so we have some extra time. I would like to use this time to remind you of tomorrow presentations. Please make sure to attend the presentations tomorrow, starting with the keynote speakers and 2 sessions like what we had today. If there isn't anything else to discuss, we can adjourn the meeting. Thank you.